and welcome to the Malvern Panalytical Web Seminar Program. My name is Linda Bradica. I'll act as your host and moderator for today's web seminar, Laser Diffraction Masterclass, the benefits of combining laser diffraction and image analysis, presented by Dr. Ann Verdin, our product manager, and Dr. Robert Taylor, a segment marketing manager, analytical imaging. In this webinar, we'll take a deeper look at the Hydro Insight, a dynamic imaging module for the Mastersizer 3000. Dr. Ann Verdin has over 10 years experience as a technical specialist supporting Malvern Panalytical's laser diffraction and analytical imaging customers. Earlier this year, she took up a role in the product management group, working with a number of products, including the flagship Mastersizer range of laser diffraction systems. So I thank Ann so much for putting the time in to talk to us today. Dr. Rob Taylor is a segment marketing manager, analytical imaging, and Rob has having spent nearly 4 postgraduate years firing lasers at precious metals. Rob moved into developing electrochemical and spectroscopic applications in pharmaceutical development. The following 8 years was a journey into measuring properties for lead optimization and pre-formulation, where Rob gained valuable knowledge about drug release from oral solid dosage forms. Here, particle size and shape are critical and to controlling the performance of drugs in vivo. After this, Rob made the move to Malvern Panalytical, where he is discovering the application and nuances of measuring particle morphology and how this impacts both the performance and quality of not only pharmaceutical products, but also food, advanced materials such as metal powders, and building materials. As a technical specialist and now as a marketing lead for Morphology 4 platform, Rob is keen to hear how your process utilization particle size and shape and wants to share knowledge on these applications. So please get in touch if you have any questions on these. He has a PhD in utilizing spectroscopy and electrochemistry, experience in measuring drug properties, lead optimization and pre-formulation, correlating particle size and shape to product performance and quality, like today's topic, supporting your technical needs in the applications of particle morphology. So get in touch with him if you like. I can see people are taking the poll. Please take a moment to answer this poll, and I'm speaking to you, our live audience. If you're listening on demand, because we record all of these web seminars, you won't really see the poll, but we'll talk about it in just a bit. So while people are doing this, I'm going to get our presenters on the line here. Hi, Ann. How are you doing today?
Hi, Linda. Very well, thank you. How are you?
I'm doing great. Thanks for being with us. And Rob, how are you doing?
Likewise, yeah. Very good, thank you, Linda. Hope you're doing well.
Yes, thank you. So Ann, while people are taking this poll, can you give us a little bit of insight into the insight?
Yeah, so this afternoon or this morning, wherever you are, we are going to look at how laser diffraction and image analysis combine to give you better insight or better understanding of your materials. So what I'll be covering is why you might want to combine laser diffraction and imaging technologies, why they're such good complementary techniques. I will then tell you a bit more specifically about the Hydro Insight, how it works, how it combines with the Mastersizer 3000, and then look at the types of results that we get from that system, so how you can use them alongside your laser diffraction particle size data. And then I will hand over to Rob to look at some case studies.
All right, Rob, can we hear a little bit about these case studies?
Yeah, sure. So this is going to be focused on mostly how we go about optimizing the development of laser diffraction methods using this integrated imaging technique. So we're going to cover a little bit about sort of how we can use that for method development, the sort of things that we would expect when if we have some unexpected results. So what can we do with imaging to sort of help chase down those problems? And then also, finally, I'll cover a little bit on method transfer, which is quite apt for those people who are, moving from, say, the Mastersizer 2000 to 3000. But in this case, I'll also focus on sieves, moving from sieving to a laser diffraction type method as well.
Excellent. Well, thank you so much. As you heard me say before, we do record all of our web seminars. They're placed in our library on our website under the Learn tab, so you can have a look at that. And I did mention earlier, we do have that blog site, Materials Talks. Have a look at that. It's a great place to get complimentary educational materials on the subjects of your interest. So in the interest of time here, I'm going to go ahead and close this poll and share the results with all of the live audience. Now, people are still filing in. We've got a large global audience with us here. Over 100 people have joined us live. And the data is just wrapping up on this poll. Okay, so poll results. So I've just shared them on the screen there. Let's have a look. Do you see them? The results, Anne?
Right, so we've quite a few, more so than 3,000 users and a few 2,000 as well. So it's interesting results, yeah. And the majority of the people here are working in R&D and a few in QC. So nice spread of people with different instruments and different working environments.
Yes, and I will handle those requests for demos. I'll get those across to our sales teams in all the different areas of the globe. If you have a particular urgent request, you can get in touch with me by emailing events@malvernpanalytical.com with your request. And so for those of you watching on demand, simply email events@malvernpanalytical.com to make your email request, or simply just go to our website, click contact us, or request a demo buttons are there as well. So thank you for interacting. We hope you all get your questions together and have found that Q&A icon. I'm going to get the controls over to Anne so we can begin.
Okay, thanks, Linda.
Welcome.
Slides going. Put it into full screen and hopefully that should have worked.
Yes, looks good.
Okay. Fabulous. So as I covered this a little bit already, we'll look at why we want to combine laser diffraction and analytical imaging, why that's a useful combination of information to have. We'll look specifically at how the Hydro Insight works and how that combines with the Mastersizer 3000, the types of results that you get and how you can process those results to get specific sorts of information, and finish off with a few different case studies of looking at laser diffraction results alongside analytical imaging. Okay. So we'll start off talking about why particle size and shape are important. And that's largely because it affects how a material behaves. For example, if you've got smaller particles, they have a higher surface area. But also if those particles have a rough surface, they're going to have an increased surface area compared to a smooth one. And this will affect things like dissolution rate in pharmaceuticals or reaction rates in batteries. Particle size and distribution also affect how particles pack together. So if you've got a particle size distribution, then the small particles can fit in around the larger ones and increase the maximum packing fraction. But it will also matter what shape those particles are. So if they're spherical, then they will pack together more efficiently. So that will have an effect on things like the strength of 3D printed parts using those sorts of powders. How particles behave in a fluid will also depend on size as well as things like elongation. So if you have long, thin particles, they will align differently in a fluid and deposit differently, for example, in the lungs. And any process that moves a powder from one place to another will be affected by both particle size and particle shape. So finer particles are more sticky, and also the more irregular shape the particles are, the more likely they are to interlock and cause problems with flowability. So what laser diffraction can do is give us the particle size distribution of a huge range of different materials and really quickly and flexibly. Adding particle shape data to that gives us, in addition to that bulk information about the size distribution, it gives us the individual particle detail and further information about the shape of those particles and how that affects the way that they behave. So that's why we would measure particle size and particle shape, and why the bulk information for example, from laser diffraction, it combined with the individual particle detail from image analysis is really useful. We've talked about in that slide why measure particle shape. In this slide, we'll look at the sorts of information that particle shape gives you. So when you have an image of the particle, what sort of information can we tell from the shape of those particles? So for example, if we have a smooth surface to the particle, is it a single particle compared with a more complex structure of an agglomerate? Do we have a particle that's close to circular, or is it more elongated? So in terms of how materials pack together, that becomes very important. Again, looking at rough versus smooth surfaces. So we're looking at anything to do with a reaction rate. If you've got a rough surface, you've got a greater surface area, whereas if it's smooth, it's going to have a lower surface area. We can also start to look at how thick or thin particles are based on whether they're letting light through or whether they're much darker. So these are the sorts of information that we can get from looking at particle shape and start to interpret in terms of the behavior of the material itself. So that's what it might be able to tell us. What we'll look at next are how we go about measuring particle shape and how we use image analysis. So there are two common types of systems used for image analysis. We use static imaging, where the sample is dispersed onto a substrate and it moves past the sensor, and dynamic imaging, where the sample flows past the sensor in suspension. And that's what we're going to focus on this afternoon with the Hydra Insight. So it's a dynamic imaging accessory. So it's measuring particle size and shape with the particles in suspension as they flow past the sensor. So that's illuminating the sample with a strobe light, which essentially freezes the image, and collecting that image with a digital camera over the other side. So what we've got on this slide is a video of the sample flowing through the Hydra Insight, so you can see the samples as they pass past the camera. So that's how we take the images. Once we've collected those still images, we extract the individual particle images from the background, so we can tell what's particle and what's the background image. And then we start to measure the different size and shape parameters from those images. So we can start to look at size in 2 dimensions. So you could look at particle width, for example, or particle length. And then also to calculate shape parameters based on those images. So we're measuring shape information such as aspect ratio, so how long and thin the particles are, or things like circularity, so how close is the particle to a perfect circle, and also parameters that look at the surface properties like the smoothness. So that's what dynamic imaging does. We've got the sample flowing past the sensor, we collect images as they go past, and then we start to extract size and shape information from those images. For a quick refresher on laser diffraction, if you want more information about the details of how laser diffraction works, there are many other webinars on our website you can listen to, but this is a very brief recap for those of you who are not familiar. So laser diffraction doesn't measure particle size directly. It's a light scattering measurement. So what we measure is the intensity of scattered light from the particles as a function of angle. And the particle size is interpreted from that light scattering pattern, which is what we've got on the left-hand side of the slide there, by looking at where those bright rings are in the diffraction pattern. So if you have big particles, they scatter light at narrow angles, and you get that bright ring close to the center of the diffraction pattern. If you have smaller particles, they scatter light to much wider angles and with lower intensity, so you get a much more diffuse pattern. And that's the basic principle on which we get size information from measuring that light scattering data. What laser diffraction is as well is it's an ensemble technique. So the scattering pattern we have here is made up of lots of particles in the laser beam. And any measurement that you make on a diffraction system will be of hundreds of thousands of particles. So as they recirculate through the system, each scattering pattern is created from hundreds of thousands of particles. And what that gives it is excellent reproducibility. we're always sampling lots of material, so we get good reproducibility in the measurements. In terms of the data that it produces, laser diffraction reports a volume equivalent spherical diameter. So the particle size that we report in any of the pages that the systems produce is the diameter of a sphere that has the same volume as whatever shape your particle happens to be. So like quite a lot of particle sizing techniques, it's making the assumption that all the particles that we measure are spherical, which, as we've seen in some of the pictures already, isn't always the case. One of the great strengths of laser diffraction is the broad dynamic range. So you can measure particles from below 100 nanometers in size up to a few millimeters in size. And that wide dynamic range gives it a huge range of applications. So it's a real strength of the technique is that it can measure a lot of different types of materials really quickly. So that's a brief refresher on laser diffraction. And on this slide, what we'll look at is why we would want to use these two techniques together, why they work so well together. So laser diffraction and analytical imaging are very often used together in separate systems. They are complementary techniques. They're used side by side, usually to help get a full understanding of a material's behavior, but also to provide backup to method development processes, so to validate the state of dispersion, to give a bit more understanding of what state the material's in. So this slide illustrates why they are complementary techniques. So what you'll see is that the strength of laser diffraction, as we've talked about briefly before, is the wide dynamic range. We can measure particles in a wide range of sizes, particularly submicron measurements and also polydispersed distributions. You can have particles that span the whole range from submicron up to millimeters in the same measurement. And those are relative weaknesses of dynamic imaging. It is a bit more limited in terms of dynamic range and its ability to measure very small particles or very polydispersed distributions. Whereas what dynamic imaging will give you is the individual particle detail that we can't see in an ensemble technique. It will give you a bit higher resolution if you've got very small populations of a certain type of material, again, which we don't see so well in an ensemble technique. And being an imaging measurement, it will give you that particle shape information. So the relative strengths and weaknesses of both techniques balance out quite nicely, which is why they're very often used side by side anyway, and why it makes great sense to combine the two. So next, what I'll cover is the Hydra Insight, which is a new accessory that we have for the Mastersizer 3000 that will provide dynamic imaging alongside your laser diffraction measurements in wet dispersion using any of our recirculating dispersion units. So that will let you get your size distributions from laser diffraction alongside the shape information from dynamic imaging. So just to show you how the two systems fit together, we've got our Mastersizer with a wet dispersion unit set up here, the Hydra MV in that case. So what you'll get on this side is that the dispersion unit for the Mastersizer, so the sample will then flow from the Mastersizer to the Hydra Insight through the measurement cell there for the flow cell, and then through to the measurement cell in the Mastersizer 3000. So in the Mastersizer, you'll measure your light scattering data from the laser diffraction measurement. That will give you the particle size distributions and also all that useful trending information in terms of understanding how well your material's dispersed. Alongside that, we'll get the images of the dispersion from the Hydra Insight. It will produce thumbnail images of each of those individual particles, from which we can build all these different histograms and statistics on the size and shape data. So it allows you to get all of this information on the same sample, the same dispersion. So that's the real benefit of combining the two systems, is that the sample's in the same state of dispersion when you make these two different measurement types. So to give you a little bit of detail on the hardware, we have a 5 megapixel digital camera As standard, it records at 14 frames per second. There's a xenon flash lamp to illuminate the sample nice and quickly so we can stop the images of the particles as they're flowing through. And the flow cell in the Hydra Insight is 1500 micron wide. So that is wide enough for the majority of the samples that we measure in wet dispersion on the Mastersizer 3000. And we can use the Hydra Insight with any of the recirculating wet dispersion units on the Mastersizer 3000. So that's how the hardware all fits together. In terms of the imaging measurement, so once we've collected the images on the Hydra Insight, they are then processed, and you can choose how you process those images, particularly in terms of which particles are included in the analysis and which are not. So part of that's to do with the fact that we've got quite a wide flow cell and not all of the particles are going to be in focus. So there's the ability to choose which particles you include and which you don't include. So we can do that based on focus. So on this image, if we skip to the next slide, you'll see some of the particles now have red crosses next to them, and that's because we've changed the focus rejection. So we've decided that those particles are not in focus enough and we don't want to include them. So you have the choice as to how you set that up. There's also the ability to select particles based on the shape. So if you're particularly interested in the, say, highly spherical particles, you can choose to exclude particles that are less than highly spherical. And that's done here. You can see the blue cross next to particles that have been excluded because of their shape. You can also filter out particles for other reasons. So looking at opacity, if you just want to look at darker or brighter particles, and usually anything in contact with the border of an image will be excluded. So there's quite a lot of flexibility in terms of how you set up the imaging measurement. And next we'll look at what results we get, what types of parameters and the size range over which each system can measure. So there are two variants of the Hydra Insight. It will, you can choose either to use a low magnification lens. So one system comes with a measurement from 10 to 800 micron, which is approximately 2 times magnification. The other system has a standard magnification lens, which is approximately 8 times and measures from 1 to 300 micron. In those size ranges, it will produce all of these different size and shape parameters. I'm not going to read them all out because there's about 30, but you can see there are those based on the circle model of a particle, so circular area diameter, which compares well to the volume equivalent diameter you get from laser diffraction. There are also parameters like the shape for circularity and smoothness, for example. We'll come back to other parameters as well, like the bounding rectangle width when we talk about comparing to sieving. And there are other parameters that you'll be familiar with if you've done some imaging, so the Ferret diameters, etc. So there are lots of different size and shape parameters that it will calculate. And if we look in the next couple of slides at how you can present that information and start to interpret that and gain knowledge from it. So we'll look over the next couple of slides at how you present the results and the flexibility of that. So first of all, I think the thing that grabs my attention most of the time is just the dispersion images to start with. Being able to see what's going on inside the Mastersizer, you can see what your particles look like, how well dispersed they are. And you can save individual frames as you're doing your method development, or you can set up the system to automatically record a certain number of frames in each run. Once you've run the measurement, it will produce these particle thumbnails. So you've got an image of every particle that you've included in your measurement. They're sorted by equivalent circular diameter, but you can choose which parameter gets displayed underneath. So if you want to look at the highly circular ones, for example, you can put the circularity underneath and put on some filters to look at those. You can also present this information in terms of histograms, so choose your size or shape parameters to display in the histograms, and they can be weighted by number, surface, or volume, and the volume will give you a bit more comparability to what you get from the laser diffraction measurement. There's also the ability to apply some filters to the data post-measurement, so you can focus on whichever area of the sample is most interesting. For example, if you want to look at elongated particles or spherical particles, you can put shape filters on to narrow that down. You can also create correlation plots. So with the data that you produced with all those particle details, you can plot say two parameters against each other, whether that's size or shape. So often we look at circularity against elongation. That can be quite a handy type of measure or aspect ratio. And that helps you to identify multiple populations within a sample, so you can see where those dense areas are with different amounts of particles. And what Rob will talk a little bit about later on is that there are correlation methods for sieves. So we have some sieve correlation tables that give you the size information. So you probably look at something like the width of the particle, because that compares better to sieving. And that lets you put those particles based on their width into the different sieve sizes. And that can help you to transfer methods from time-consuming sieve measurements to quicker measurements by laser diffraction, using that additional particle shape information that helps you correlate between the sieving and diffraction. And finally, there are numerous ways of presenting this data, whether it's exporting it to text files, creating reports with thumbnail images, tables, and distributions. So there's a lot of flexibility in terms of how you can handle the data that's been created by the Hydro Insight and how you can present that to help you to better understand your materials. So hopefully I've given you an introduction here to the Hydro Insight and why you want to combine laser diffraction and image analysis data. And I'll hand you over to Rob, who's going to cover the case studies in the second half of the presentation.
Okay, thank you, Anne. Okay, let me my presentation up. Bear with me a second. Okay, so hopefully you see that in presenter mode.
Looks good.
Excellent, thank you. Right, so yeah, thank you, Anne. And hopefully then you've all been listening now and you can understand how the Hydro Insight works and how it sort of fits alongside the Mastersizer 3000. And what it's intended for is to be a tool which will help you understand something about your dispersions and give you some indication as to how to develop methods and just looking for sort of any anomalies that might come through. And indeed, if you're looking to sort of move your method across between different platforms, so whether that be the 2000 going to the 3000, we've got examples of that, but I'm not going to present that today. But would you have an example of how you might go about it if you are changing from, say, a sieve to laser diffraction and what might be relevant? Okay, so I'll take you through to the end of the presentation, and let's just get on with the first one, which is around method development. And what I would say is that the stage of where you are trying to disperse your sample is possibly, at least from my view, is one of the most critical stages of your method development. So actually how you prepare and then present your sample to the instrument is really going to dictate how sort of robust your method is, and of course how sensitive it is to your process. So what we often find is that when it comes to robustness, people often stumble when it comes to not having quite the best method for dispersing their sample. And of course, you know, this could lead to sort of problems further downstream. So it's always worth just exploring around the design space of how to disperse samples and making sure you select the most robust one, but of course making sure that it's sensitive to the thing that you are trying to understand. So the Hydro Insight, it's intended to sort of work with wet dispersions. And so in that case, the first thing you're going to come across is what dispersion you're going to choose, of course. And so A number of do's and don'ts here, but the first one would be is that you don't want to choose a dispersant that's going to dissolve your sample, of course, because you're going to get a decrease in the particle size distribution. So just making sure that it's not a very powerful solvent in that regard would be a first decision. Bubble free, of course, bubbles are particles after all, and they will be measured if they are there. So if you do have bubbles, then of course you can just degas your dispersant. But making sure that's the state that you have is also critical. Viscosity, these fluids are moving around. They need to move from the dispersant unit through the hydroinsight cell into the laser diffraction cell and then back again. So if it's too viscous, that simply won't happen. So making sure you have good viscosity is important there too. Refractive index. I mean, both of these are optical techniques. So if you have a refractive index of your dispersant very similar to that of your analytes, your particles, then you're simply not going to see them. So making sure you have very sort of different refractive indices between the two is important there. And finally, chemical compatibility. So yes, there are chemical compatible options with both the Mastersizer and the Hydroinsight. So just make sure that you've got the relevant one that's been selected. And of course, to ensure that, just get in touch with us and we can give you some further guidance on that. So that would be looking at what dispersants to choose, and just a very quick test you can run is to do a beaker test, or in this case it would be in a vial. So here you just take a very small sample, put your dispersant in with it in the vial, shake it around and just see what you get. And let me just bring up my laser pointer. What you can see just on the left-hand side, we've probably seen this image before if you've watched any of Anne's presentations previously, or mine indeed. But here, you see you've got a separation. You have material that's floating on the top. You have material that's sedimented, and something in between. So clearly, not a very homogeneous dispersion there. And in that respect, you can't really expect much in the way of a robust method. But on the right-hand side, all that's happened here is just a small amount of surfactant, not too much, not in excess of the critical micelle concentration, but just enough to kind of wet the surfaces and just to allow the dispersant to interact more freely with the solid material. And that of course gives you a much more homogeneous dispersion, and that's the kind of thing that we're after. So in this first stage, just do this quick test. It's very short, and it will give you sort of a very quick idea as to what dispersants are going to sort of give you the best results. And then, of course, you can then just put it into the system and start collecting some data. And now that we have an imaging system in tandem with the laser diffraction system, you can start seeing what the particles actually look like. And this is really sort of at the top and bottom of what we're trying to do here. So in this particular case, we have what looks like quite a broad-looking distribution, a very polydispersed system. We have some, very large particles there, as well as some very fine material. So quite polydispersed. And of course, the next step is to say, well, how stable is that dispersion? Sorry, excuse me. I just need to get rid of a pop-up there. Right. Okay. So. How stable is that dispersion? Of course, we can apply some kind of energy to that. It could be just stirring, but in this case, you can apply some sonication. And so you can see there that you put some sonication in. That's a form of energy to sort of just disperse those particles. And now we can see what the effect of that is actually on the particles themselves in terms of their images. Okay, so we've got a much finer dispersion. It's probably a bit more monodisperse. We've got rid of some of this big material there, and so that's just the impact of sonication. And it's a good way to visualize what it is that's actually occurring in the system. Once you've done that, of course, then you might want to think about stabilizing that as a dispersion. So it's not unknown that if you apply sonication or any other kind of high energy form of dispersion, that it can simply return back to what it was. It can re-agglomerate. And so just stabilizing that using admixtures. We've got a couple of examples here. This is simply where you have, just using some electrostatics just to sort of repel the particles from each other. Okay, so here we are again. So we have, going back to the beginning, we have a very polydispersed system, and you can see now we have some laser diffraction data. This is the particle size distribution or the interpretation of that. And so we have, it's quite polydispersed. We have some fine material, some coarse material there. And as we put this sample into the dispersion cells, we start to see a change, and this is reflected in what we can see in the middle of the screen, which is the distribution values, the D90 in black here, the D50 in green, and then the D10 in grey at the bottom there. We can certainly see how the D90 and the D50 are changing with time. So that's just an impact of the stirrer, and of course, if you allow the stirrer to continue, eventually it'll reach some kind of equilibrium. So in this case, now you can see some the video of that dispersion going around there. So of course you couldn't allow the stirrer just to continue and get to the equilibrium, or indeed you could apply the ultrasound to get down there a lot quicker, and that's really sort of the purpose behind it. And now we can see on the right hand side we have a video of that a lot more dispersed system. Okay, there are a few larger particles flowing through there, but by and large we've got something that's a bit more monomodal in appearance, and indeed, if we now take a look at the dispersion, the actual distribution, we can see by comparison to what we have on the left-hand side, it's a lot more monodispersed, a lot finer in size, and so we've got a visual representation of that change. And now, what happens there on in is is that a stable dispersion? And then, of course, ask yourself the question: is that relevant to the process I'm trying to get a metric on? We've come across some people who have used sonication. They've got a nice, robust system, but they've lost all of that relevant information about their sample. So it's always worth considering that before you overdo the sonication. Okay. So moving on to the next part, which is really looking at sort of troubleshooting or trying to understand, something's changed or something new has come in. What's the cause of that? And here's a good example. We see a report on the screen here. We can see a nice sort of primary mode around 10 microns in size. And then we have something emerging here around about 100 microns in size. So often the question would be, well, what is that? What can I say that could be? I mean, it could be something that's agglomerated. It could just be a primary particle, but now it's oversized. It could be a contaminant, and of course, if your contaminant is visually quite different to the rest of your sample, then it might well be that image analysis will pick that up. And then, as I mentioned before, it could just be bubbles. So these tend to be more transient in nature. So you just degas the system, and this can help to remove. Okay, so again, we've got a nice video here of just some particles flowing past the sensor. And it might not be immediately apparent here, but we've got, broadly speaking, reasonably nice distribution, but you might just see flashing through every now and again some needle-like particles. Okay, and so what we can do then is we can collect individual frames, and by doing so, you can see here now we've captured one of these needle-like particles flowing through. Okay, so we can see it's not representative of the rest of the material that we're measuring there. Okay, so of that distribution then, okay, as I mentioned before, we have this, the main mode here centered around 10 micron, and something else that's occurred at 100 micron. And of course, because we have the image analysis function, we can isolate these particles. And as it turns out, it was those needle-like structures that was contributing to this much coarser mode that had emerged there above the main mode. Okay, so that's just an example of how you can use sort of an integrated imaging system to sort of help elucidate these kind of differences, or in this case, a sort of a bimodal system. Okay, so onto the final section here. This is now looking at method transfer, but it's also with a particular application, which is in metal powders for additive manufacture. And again, some of you may have come across some of our presentations in additive manufacture before and already have a good understanding of why this is relevant. But just to briefly cover this again, I mean, particle size, as we know, for most materials, has an impact on flowability and packing density. And it's no different for additive manufacture, particularly those methods whereby you have a layer from which you 3D print a 3D shape. And so creating that layer, you have to flow the powder onto a powder bed, and then that layer of powder has to have a certain density. So making sure you have the right size distribution to optimize that flowability and packing density is critical for that. But also, so is shape. So we see here in the figure on the bottom right corner now. So we have a function of fractional density versus sort of a shape, a particle shape. And you see there that the circular or spherical ones give you the most optimum density, whereas the sort of more irregular type shapes tend to have much lower density. So again, controlling size distribution and, of course, shape is a critical element for additive manufacture. So we incorporate the Hydra Insight here. We get a nice distribution, a size distribution from our metal powders. In this case, it's a 316 stainless steel. And similar to the previous example, we have this kind of bimodality that's emerged from the laser diffraction data. And again, we have sort of a mode, this time centered around between 30 and 40. We have this additional coarser fraction, this coarser mode that's now emerged around 110 microns in size. And so we have this, we have our Hydra Insight integrated module, and we can see now we get orthogonal type data here. So we get very similar sort of size distributions. And this confirms again that we have this rather large fraction that's emerged here as well. And so when we take a closer look at these types of particles, and you can see now some of the thumbnail images that we've got here. Okay, some of these are primary particles. So these are nice spherical in shape. But they're large in size, and it would bring into the question, do you have the right sort of quality of powder here? Is this the right sort of material that you need for your process? But also, you notice that some of these are sort of satellited materials, or sort of satellited particles, sorry. Some of them are irregular in their shapes, and this leads back to that question about, well, if they are irregular or satellited, is that going to give you the best flowability and the best packing density to form that powder bed? Again, this leads onto the method transfer element to it, and this is where we have the sieve analysis, and this comes back to what people are doing in additive manufacture. They tend to have two methods deployed for looking at particle size, and one being sieve and one being laser diffraction. And the reason why they like sieving is because it's able to pick up the one or two very large particles compared to laser diffraction, which is more of an ensemble technique. So it will, if you only got a few particles that are much larger than the main distribution, then maybe you won't see them quite so clearly with laser diffraction. But apparently you do with sieves, and so this is why people are still interested in using sieves. However, we feel that with a combination of an imaging platform as well, you can see these anomalous large particles, or the strangely shaped ones, or indeed the occasional contaminant that comes through as well. And so this is why image analysis is also an interesting technique used in this area. And so what we've got now is the ability to do a sort of method transfer between sieve and laser diffraction, and we can do this through the imaging process. So that what this table is showing you there is that we have a size distribution of specific bands that relate to a sieve analysis. Okay, so it might not be these specific bands per se, but you can select size fractions that relate to your sieve stack. And you'll get a percentage based upon, in this case, an equivalent circular area. And that's what you would get from sort of a laser diffraction method. It's based upon a spherical particle model. But of course, compared to a sieve stack, that's actually more sensitive to the second largest dimension. As you see from the animation on the right-hand side, you see that particles can orientate themselves to get through the sieve aperture. And so in fact, it's more sensitive to that second largest dimension. So with that in mind then, you can use what Anne referred to earlier as the bounded rectangle width, which is more sensitive to that second dimension. And now, of course, we get a different profile of the relevant percent weights that are coming through from these sieve fractions. And interestingly, when you compare these two, we are starting to see some considerable differences between them. So up to sort of 8% differences between them in some areas. And this immediately indicates that actually the spherical model is not quite right. So we do have some irregular shaped particles there that are in this system. And so using sort of a bounded rectangle width shape parameter can actually help us to give a much more representative distribution based upon sieve. And so this is how you can use that image analysis technique to give you a bit more information as to how you might transfer between the sieve to laser diffraction. Okay. So just in summary then, hopefully you've seen there sort of what the Hydra Insight is about, how it sort of sits alongside the master sizer 3000. And hopefully I've covered there how you can use that to sort of optimize your method development, how it gives you some clues as to what the best way to develop the methods is. And then doing some troubleshooting. So if you have some anomalous particles, or if you have a fraction that's bigger than the main mode, then you can use image analysis to sort of resolve what's happening there. And then just generally understanding what your materials look like. This can be a really useful thing to do if you've got some powder flowing through your system. What do these particles actually look like, and how does that represent the process from which they've come from? And then, of course, finally looking at if you are thinking about transferring methods, this is particularly relevant to those transferring from 2000 to 3000, or indeed going from sieve to a laser diffraction method. Then again, image analysis can be useful for that. Okay, so with that, I'll thank you very much for your time. Hopefully it's been a useful webinar, and with that, I'll pass back to Linda for a Q&A session.
Thank you so much, Rob and Anne. And as you heard Rob said, now the floor is for you, those live attendees with us that have questions. We're going to get you your answers right away. And for Anne and Rob, some of the questions are in the chat, and then some of them are in the Q&A facility. So I'll start with the first one that came in from our audience very early on. 5 minutes in was, I'm from Brazil, and I look for how to improve my particle size analysis. And I want to focus on finding more repeatability and accuracy. So advice for this person, please. Anne, you are muted. Did you begin?
Thanks, Linda. So yeah, a lot of what we covered in terms of method development will help with improving repeatability, reproducibility, and accuracy of the measurements. So as Rob covered in the method development section, understanding how your materials disperse, making sure that dispersion is stable and repeatable will go a long way in terms of making sure you get repeatable measurements and robust measurements. There are a lot more webinars that go into that process in a lot more detail. We've done a few laser diffraction masterclasses, some specifically about method development. So there'll be more detail there.
I would definitely have this person go to the Learn tab, go to recorded content, search by masterclass. We did a beginner, advanced, intermediate, was it last year? Then Dr. Alan Rawl has one on help me remember, and it was
on the optical properties.
The optical properties, I think, is a really good place to start if you're just ramping up your education on use of the laser diffraction instrumentation. Thank you for that. All right, so next question is it easy to change over between the high and low mag lens?
So those are separate systems. So we would advise you as to which lens would be appropriate for your application. So you would either have a low mag lens or a high magnification lens. So most of the applications we've shown today were using the low magnification lens, so going from 10 to 800 micron. But it's something you would choose at the configuration stage and not swap between later on.
All right, excellent. Well, this next question said that it would be very helpful if both lenses could be combined for the histogram, but that's not the way this accessory works.
No, that kind of takes us back to the strengths and weaknesses of laser diffraction and analytical imaging. So the width of the dynamic range being a strength for laser diffraction and not so much for image analysis.
Right, right. Okay, then we've got a question that we all knew we were going to hear. How much would it cost to incorporate the Hydro Insight with the Mastersizer 3000? I think we all heard this is a global audience, so I'm going to take that question and get it to a specialist within this individual's area of the globe for them to reply back. So I'll get that message across today for that individual. Thank you for the questions. Please keep them coming. We do have 9 minutes left to answer your questions right on the spot here. If you're listening on demand, simply email us your question at events@melbournepanelytical.com or click the contact us from our website. Okay, is it being recorded? Yes, we're recording this. It will be posted in about 2 business days to our website. When did this accessory become available for the Mastersizer 3000?
So we launched this in July, so it's not been available for too long. So we did a launch event at the beginning of July. So yes, not too long, quite new. We're excited to get using it for different applications.
All right, excellent. And for those of you that want to quote, go right to our website and you'll get somebody in touch with you soon. Let's see. Question is, sometimes have a small sample volume. Which is the smaller sample volume to be used with the Mastersizer 3000?
Yeah, okay, so we have a range of different dispersion units for Mastersizer 3000, both wet and dry. So the recirculating wet dispersion units, so something you could use with the Hydro Insight, it would be something like the Hydro MV, which is the medium volume, which takes 120 mils of dispersant, or the Hydro SM, which can go down to about 80 mils of dispersant. We do have smaller wet dispersion units, but that wouldn't work with the Insight because it's just the flow cell in the Mastersizer, for example. So if you've got a really small quantity of sample, so dispersing into 6 or 7 mils of dispersant, then that would just give you the diffraction measurement in the Hydro SV. So depends how little sample you've got and what you want to do. But I'm sure we can talk in more detail when you want what materials you have.
Excellent. So get in touch if the answer has got you asking more questions. Next question. Currently using the Melbourne Panalytical Mastersizer 3000 with the Hydro LB for this method. Is sonification always required?
Shall I take this one? So I mean, I'd have to see what method you're actually running there. But I mean, certainly you can set up an SOP, a standard operating procedure, to use a sonication, and indeed that will be run every single time you run the SOP. So that's up to how you develop the method, I suppose. It's my preference to explore using a simpler SOP. So if you can avoid using sonication, I'd say in the long term that will probably serve you better. But if you need to, then that's part of the SOP, and so be it.
Great, thank you. Here's a nice question for somebody working with ice cream. So that's nice for the end of the summer question. What are some of the parameters such as obscuration range, stirrer speed, refractive index that are suitable for food samples such as ice cream mix to measure the oil particle size? Let's see. Would the sample parameters be still the same when using melted ice cream samples?
Yeah, we have measured melted ice cream before. It's kind of, I guess, similar to measuring cream or milk in that your refractive index is possibly a bit of a balance between the protein and the fat, but you can put in a refractive index that's closer to the fat optical properties. Stir speed for something like an emulsion like cream or ice cream doesn't have to be too high. It's probably not going to sediment or fall out. So yeah, those are primarily the optical properties and the obscuration range, because you've got some quite small particles there. So whether you're going to start looking at things like multiple scattering if you have too much sample in there. We have some application notes about dairy applications. I think it's more about milk than about ice cream, but a lot of the parameters and the approach to the analysis would be quite similar. But
Yes, thank you.
any of the general application notes about method development will tell you which bits are important, and the milk will give you an idea of what the results might look like.
Very good. Thank you, Anne. And here's the question I knew we were going to come across. What is the difference, or is there any difference between the Hydro Insight and the Morphology either 3, which I saw, or the 4ID?
Shall I take this one?
Yeah, you can get that
Please.
one.
So yeah, I mean, I think Anne sort of briefly covered this at the beginning. So the Hydro Insight is a dynamic imaging system. So compare that to the Morphology G3 or the Morphology 4, which are static imaging systems. And the difference is simply that with dynamic imaging, you're sending your sample, your particles past the sensor, whereas it's the other way around for static imaging. But in the practical sense, there's also a fair bit of difference too. As with dynamic imaging, you have particles that are flowing past, they can be a bit more challenging to actually image. Compare that to the static imaging systems of the morphology. You often find that you can get much clearer images, the resolution is much improved. But there is some offset there as well, because dynamic imaging can generally measure many more particles in a shorter time frame. So it's a balance between sort of resolution and time for analysis, I would say, is the two main differences in the application side.
Yeah,
Right, and then
so-
the ID part, the Raman is totally different.
Absolutely. So with both the G3 and the Morphology 4, they both have the variants where you can have Raman integrated into those systems. And of course, what's nice about that is that you can return to particles and you can identify their chemical makeup with the Raman spectroscopy. But because because the particles are themselves moving in a dynamic imaging system for Hydro Insight, it wouldn't be possible to return to any particles with Raman. So we don't have that option for the Hydro Insight.
And you were going to say, Anne?
Yeah, I was just going to mention the sample preparation aspect of it. So with static imaging systems, morphologies, you've got a lot of different ways to prepare the sample, which can be a good thing and a bad thing. So you've got a lot of flexibility in terms of how you prepare the samples. But it means it is different to what you do in the diffraction system. Whereas if you've got a dynamic imaging system, particularly one that's combined with the diffraction, then you're taking the same sample onto both. So as Rob said, it depends what you want to do. There are various factors to balance up in terms of what sort of information you get and what state your sample is in.
Very dependent on your application and what those parameters that are required for your method. So very interesting. There are a few more questions here. Let's see if we can get to them in the next few minutes. What is the depth of focus, and can you adjust depth of focus? Can you automatically distinguish focuses versus unfocused particles?
Oh, I have to get back to you on the actual depth of focus there, but no, you can't change that. That will be dependent upon the lens that you choose. So we have the low magnification lens, which would have a higher depth of focus, and the standard mag lens, which would be smaller.
Yeah, and as we showed you in the slides, you can choose which particles you include. So we understand as it's going to be narrower than the whole width of the flow cell, so you can exclude particles that appear to be out of focus.
Thank you. Here's an interesting question that I don't think we can do, but I'm going to ask it. Can this imaging system be used with other brands of laser diffraction equipment?
No, so we're only supplying this with the MUS sizer 3000, so as an accessory to the 3000.
Right. So if this person wants to think about maybe trading in or having someone get in touch, I can do that. We can see what we can do for that person. Lots of thanks coming across for the webinar. And then here's a confusing question to me anyways. Will this system be available for Aero Sampler anytime soon?
So it's certainly an interesting question, and something that we'd love to look at is to do this sort of imaging on a dry system as well. But at the moment we're just looking at the wet systems. But yeah, we'd be intrigued to hear what applications you have for those sorts of samples.
Right. And then I see an interesting question, which I think we'll take offline regarding the refractive index and how that changes the particles visually. But I'd like to ask a few more questions, please. Let's see for these weeks. Let's see.
Yeah, it'd probably be quite sample specific, so we're happy.
Yeah, that would. So I'll get the details across to you, Anne. Has online diffraction index determination and laser diffraction on the same equipment? So I'm just reading it phonetically. So I guess they're asking if it is this online diffraction index determination.
So we have online instruments for laser diffraction. We don't determine refractive index for materials either online or offline, or there's other equipment you can use to do that. I don't know if that answers the question.
All right, well, that individual should get in touch if they have more questions. Here's one about refractive index. How important is it to the 3.0 micron particle size analysis? I face an issue with my 2000 and 3000 correlation, and can I fix this with refractive index?
So if your particles are about 3 micron in size, then the refractive index and the absorption index are going to be quite important in terms of interpreting the scattering data for a diffraction measurement. And it's certainly a possible cause of difference between the two systems. If you haven't got it quite right, then sometimes systems will give slightly different answers. I would particularly look at the absorption index as well. So again, it depends what your material is, how easy it is to find the refractive index values, but also to have an estimate as to what your absorption index might be. And a good way to do that is also to look at images of the particles, but at 3 micron, yeah.
And would it help, because they're trying to correlate, I guess, the two different instruments, the older 2000 to the newer 3000, maybe it's that transfer webinar information we have that might help. Yeah,
we did a whole series of webinars on method transfer, and one of the sort of case studies does look at the optical properties for a few materials and how that can affect the transfer. So yeah, that's a great resource for that.
Yeah, that was last year that we did that whole series. I think there were four or five on that. Yeah. Let's see. And just a few more here. Can this type of work also be done by Morphology G3? What are the advantages and over the G3? I think we answered that question with the comparison. If not, please get in touch with us so we can elaborate. There are so many questions here. I guess we'll just take one more here. What are the particle size limitations of the device, and can it measure sphericity of 1 to 2 mm granules? Excuse me, but I think you understand what I'm asking there.
Yeah, so
the size limitations.
The low magnification lens will do 10 to 800 micron, the standard 1 to 300. So we can look at circularity, which will give you a measure of how close materials are to a perfect circle. But I think if it's in the millimeter range, that's going to be outside of the range of this instrument.
All right, and I think this is a great question to end on. How long does it take to do the image analysis study using the Hydro Insight in tandem with the Mastersizer 3000, of course?
Practically the same as the Mastersizer 3000. So you've a couple of things to set up in terms of how you record the images, which is what we showed earlier on, but you're measuring over the same time frame as you do the Mastersizer. So it's very similar.
All right, excellent. Well, thank you so much, Anne and Rob, for putting this presentation together as we move into the fall when it gets very busy for us here at Melbourne Panalytical. I look forward to working with you again, and thank you to our audience for being here. Please know we record this. It will be up on our website in about 2 days' time. If you're listening on demand, your questions are very important. Use that email address or just get in touch with us. It's very exciting to be talking about this new accessory for the Mastersizer 3000. And now I'd like to just hand back to Anne and Rob to close today's web seminar. Just a moment of your time. When you leave the live web seminar, a survey will populate your screen. Please take a moment to answer these very short questions. It's how we can continue to improve this program and bring you topics that you're interested in. And now over to you, Anne, for a close.
Thanks, Linda, and thank you to everybody for joining us. It's been a pleasure to give you a bit more detail on an accessory we launched in July and to be able to show you a little bit more about how it works. And thank you for all the interesting questions. It's been great.
And over to you, Rob.
Thank you. Yes, just similar to Anne there. Thanks to everyone who has taken the time to watch the webinar. It's always very encouraging to see this many people who are attending. And similarly, it's great to get in touch with us and to let us know what you think. Really, this is very key information for us. So just let us know if you think it's good, bad, whatever, and we can move forward from that. Thank you.
Thank you so much. And let's see, I'm just trying to get to our last slide here. Thank you for attending, everybody. We hope you stay safe and well. We are Melbourne Panalytical. We're big on small. Goodbye.